Have you ever looked up at the night sky and kind of wondered, like, why is it dark? It's a question that puzzled astronomers for centuries. I mean, if you think about it, if the universe was infinite and unchanging with stars scattered everywhere, shouldn't the night sky be blazing with light? It's like every direction you look, you'd eventually hit a star, right? But obviously, that's not what we see, so what's going on here? Well, the answer, as you might have guessed, is that our understanding of the universe was a little off. For a long time, people believed in a static, eternal universe. It was a comforting thought, this idea of a never-ending, unchanging cosmos. But then came these two guys, Edwin Hubble and Vesto Slipher, and they started looking at galaxies through their telescopes, and what they found totally shook things up. See, they noticed that the light coming from these galaxies was shifted towards the red end of the spectrum, a phenomenon called redshift. Now, redshift happens when an object is moving away from us. It's kind of like the Doppler effect with sound. You know how an ambulance siren sounds higher pitched as it approaches and lower pitched as it moves away? Same principle with light. Anyway, Hubble and Slipher found that most galaxies were redshifted, meaning they were moving away from us. And the farther away a galaxy was, the faster it was moving. It was like some giant cosmic exodus, with everything rushing away from everything else. This discovery led to a pretty mind-blowing realization. The universe isn't static, it's expanding. The space itself is stretching, carrying the galaxies along for the ride. It's like, imagine baking raisin bread, right? As the dough rises, the raisins, those are our galaxies, all move farther apart. Now, this whole expanding universe thing has some pretty profound implications. First of all, it means that if we rewind the cosmic clock, everything must have once been much closer together. Keep rewinding, and you get to a point where all the matter and energy in the universe was packed into an incredibly tiny, dense, hot point. And that, my friends, is the Big Bang. The Big Bang wasn't an explosion in the traditional sense. It was more like the beginning of space and time itself. The moment when everything we know and see began to expand outward from that initial singularity. But here's where things get even more interesting. You see, this expansion ties in to Einstein's theory of general relativity, which revolutionized our understanding of gravity. Before Einstein, we thought of gravity as a force pulling objects towards each other. But Einstein came along and said, hold on, it's not a force, it's a warp in space-time. Yeah, I know, it sounds kind of out there, right?
Yeah.
But stick with me. Imagine a bowling ball on a trampoline. It creates a dip, right? That's kind of like what massive objects do to space-time. They warp it, creating these curves that other objects then follow. And that curvature, that's what we experience as gravity. It's not a force pulling us down, it's space-time telling us which way to go. Now, you might be thinking, okay, cool, warped space-time, but what does that have to do with the expanding universe? Well, here's the thing. Einstein's equations showed that space-time isn't just warped by mass and energy, it can also expand or contract. And in our universe, it's doing a whole lot of expanding. So we've got this expanding universe, this warped space-time, and this whole Big Bang thing. It's a lot to take in, I know, but trust me, it gets even weirder from here. Because next we're going to talk about those cosmic monsters that lurk in the shadows of the universe. Black holes. They're not really holes and they're not really black, but they are some of the most fascinating and mysterious objects in the cosmos. So buckle up, because we're about to dive into the heart of darkness, or should I say, the heart of extreme gravity. All right, so we've talked about the expanding universe, the Big Bang, and this whole warp space-time thing. But now, let's get to those black holes I promised, They're like the ultimate cosmic enigmas regions of space-time, where gravity is so strong that nothing, not even light, can escape. Now, you might be wondering, how does something become a black hole? Well, it all starts with a star, a really massive one, much bigger than our sun. These stars live fast and die hard. They burn through their nuclear fuel at an incredible rate, and when they finally run out, gravity takes over in a spectacular way. Imagine this massive star running on empty, suddenly collapsing in on itself. All that matter, all that energy squeezed into a tiny point, and boom, you've got yourself a black hole. And when I say tiny, I mean tiny. We're talking about a region so dense that its gravitational pull warps space-time to an extreme degree, creating this point of no return called the event horizon. Anything that crosses that boundary, even light, is trapped forever. So for a long time, we thought black holes were these like cosmic vacuum cleaners just sucking up anything that got too close. But then Stephen Hawking came along and, well, blew our minds again. Hawking showed that black holes aren't completely black after all. They actually emit radiation, now called Hawking radiation. And get this radiation is connected to the mind-boggling world of quantum mechanics, the physics of the very, very small. See, in quantum mechanics, empty space isn't really empty. It's filled with these virtual particle pairs that constantly pop in and out of existence. Now, normally these particles annihilate each other almost instantly. But near the event horizon of a black hole, things get weird. One particle can fall into the black hole while the other escapes, carrying away a tiny bit of energy. So in a sense, black holes are slowly evaporating, losing mass and energy through this Hawking radiation. It's a process that takes an incredibly long time, but it means black holes aren't the eternal, unchanging objects we once thought they were. But here's where it gets really mind-bending. This whole idea of Hawking radiation raises some serious questions about information. See, in physics, we believe that information can't be destroyed, right? But if something falls into a black hole, where does that information go? This is known as the black hole information paradox, and it's a puzzle that physicists have been grappling with for decades. Some theories suggest that the information is somehow encoded on the event horizon, that two-dimensional boundary of the black hole. This idea that information about a three-dimensional object could be stored on a two-dimensional surface is connected to something called the holographic principle. It's a pretty wild idea, but some physicists think it might be a key to understanding the nature of reality itself. Now, before our heads explode from all this cosmic weirdness, let's take a step back and think about the bigger picture. We've talked about the expanding universe, the Big Bang, black holes, Hawking radiation, and even the holographic principle. But what does it all mean? What's the point of all this cosmic drama? Well, for starters, it shows us just how much we still don't know about the universe. We've come a long way from thinking the Earth was the center of everything, but we're still just scratching the surface of understanding the cosmos and our place within it. But even though we're just tiny specks in this vast and ancient universe, we have this incredible ability to look out at the stars, ponder the mysteries of existence, and try to make sense of it all. And that, I think, is pretty amazing. So next time you look up at the night sky, remember that you're not just looking at a bunch of twinkling lights. You're looking at a glimpse into the vastness and wonder of the cosmos. A universe filled with black holes, expanding space, and maybe even, who knows, other universes out there. Speaking of other universes, have you ever heard of the multiverse? Yeah, buckle up because things are about to get even weirder. Okay, so we've journeyed from the darkness of the night sky to the mind-bending depths of black holes, explored the expanding universe, and even dipped our toes into the idea that information about our 3D reality might be encoded on some distant 2D surface, like a giant cosmic hologram. Feeling a little overwhelmed. Yeah, I get it. It's a lot to wrap your head around. But hold on tight, because we're about to venture into a realm that's even more mind-boggling. The multiverse. Yeah, you heard that right. Multiple universes, perhaps an infinite number of them, each with its own unique set of physical laws, constants, and maybe even its own versions of you and me. I know. It sounds like something straight out of science fiction, right? But the idea of a multiverse has actually been gaining traction in some areas of theoretical physics. You see, when we try to combine our best theories of the very large general relativity with our best theories of the very small quantum mechanics, things get a little messy. One way to reconcile these theories is through something called string theory. String theory is a whole other can of worms. But the basic idea is that the fundamental building blocks of the universe aren't particles, but these tiny vibrating strings. And these strings can vibrate in different ways, creating different particles and forces. Now here's where it gets interesting. String theory suggests that there could be many more dimensions than the three spatial dimensions, and one time dimension we're familiar with. These extra dimensions are curled up and hidden from our perception. but they could have a profound impact on the nature of reality. Some physicists believe that these extra dimensions could allow for the existence of multiple universes, each with its own unique configuration of these curled up dimensions. It's kind of like imagining a loaf of bread, with each slice representing a different universe. And here's where it gets really wild. In some versions of the multiverse theory, these universes are constantly branching off from each other, creating new universes every time a quantum measurement is made. It's like this cosmic tree with branches splitting off in every direction, each representing a different possible outcome of a quantum event. Now, I know this all sounds pretty speculative, and it is. The multiverse is still a very hypothetical idea, and we don't have any direct evidence to prove or disprove its existence. But it's a fascinating possibility, one that pushes the boundaries of our imagination and makes us question the very nature of reality. So what does it all mean? Well, for starters, it means the universe, or should I say the multiverse, is even more vast and mysterious than we ever imagined. We may never know for sure if other universes exist, but the very idea of their possibility opens up a whole new realm of wonder and speculation. It makes you realize that our little corner of the cosmos is just a tiny part of something much grander, something that may extend far beyond our comprehension. And that, I think, is both humbling and incredibly exciting. So, next time you look up at the night sky, try to imagine those distant stars as gateways to other universes, each with its own unique story to tell. And who knows? Maybe someday we'll find a way to peek through those gateways and explore the infinite possibilities of the multiverse. You know, it's been a wild ride, hasn't it? From the darkness of the night sky to the mind-blowing depths of black holes, and now venturing into the uncharted territories of the multiverse. It's enough to make your head spin. But that's the beauty of it, isn't it? The universe, or perhaps the multiverse, is full of mysteries waiting to be unraveled. And who knows what incredible discoveries lie ahead. Until next time, keep looking up and keep wondering, because the cosmos is full of surprises.